In this session, we will attenuate the vibration of a spring mass damper by designing a tune mass damper. A sinusoidal force excites the main system. We begin with the spring mass damper already grouped into a subsystem as shown.
Let's now determine the resonant frequency of the main system with a linearization template.
The template contains an embedded MapleSim component linking the Maple template and the MapleSim model.
This template lists the system's inputs, outputs, and parameters. It also contains several different linear analyses, such as the equation extraction shown here. Selecting the bode plot analysis, we can quickly approximate the resonant frequency of the main system.
This frequency is then used to excite the main system. Returning to the MapleSim model, we can set the sine wave source to operate at the resonant frequency we just identified. Next, we need to add the tune mass damper components to the main system. Simply drag and drop the mass and spring damper from the 1D translational library. The tune mass is set to 3% of the mass of the main system, while the spring and damper are parameterized with the parameter block. This lets us adjust the values in Maple. Using a Maple worksheet, we can now optimize the parameters of the tune mass damper. We assign the model structure to a variable A. We then use the parameterized spring and damper values in generating a compiled procedure. The compiled procedure returns numerical results at discrete points in time for a given set of parameters. We extract the compiled procedure's output using the API commands. To obtain a baseline response, we simulate the model with a first estimate of the tune, spring, and damper constants. Now, we can determine the optimal spring and damper parameters. Let's write a cost function. This function will add the magnitude of the vibration squared at each point returned by the compiled procedure. Using a Maple command, we can minimize the cost function to obtain the optimal spring and damper constants. Next, let's simulate the model with the optimal values we just found. This reveals that the vibration has been significantly attenuated. We then send the optimal parameters back to the MapleSim model. Returning to the model, we can see that the parameter block has been updated with the new spring and damper values. Let's now simulate the model. The simulation results match the attenuated response in the Maple worksheet.